People ask me about flying saucers, and I always find myself in a funny position. Because, on one hand, the universe is so staggeringly large that it would be almost absurd to think we are the only thinking creatures in it. The numbers just don't support that kind of cosmic loneliness. But on the other hand, when you sit down and actually work out the physics of getting from one star to another, you run into walls. Not psychological walls, not political walls, but the hardest walls in nature, the laws themselves. And those laws don't care about your civilization's ambitions, your technology level, or how many millions of years you have been at it. Let's start with the most obvious thing, which is also the thing people most dramatically underestimate: distance. When I say the nearest star to our sun is about 4 light years away, people nod like they understand. But they don't, not really. Because a light year is not just a big number. It's the distance light covers in an entire year, traveling at about 300,000 kilometers every single second. Now, light never gets tired. It doesn't need fuel. It just goes. And it takes 4 years to get to the nearest star. Not 4 years at highway speed. Not 4 years in a rocket ship. But 4 years at the absolute maximum speed that anything in this universe is permitted to travel. The fastest spacecraft humans have ever launched, the Voyager probes, are moving at roughly 17 kilometers per second. Now, 17 kilometers per second sounds fast. It is fast by any human standard. But compared to the speed of light, it's nothing. It's embarrassingly small. At that speed, Voyager would take about 75,000 years to reach the nearest star if it were even pointed in that direction. 75,000 years. The entire recorded history of human civilization is about 5,000 years. So we're talking 15 times the length of all of recorded history just to reach the closest possible neighbor. Now here is where the physics gets genuinely interesting, because you might say, well, we just need better engines. We need to push harder. And yes, you can do better than Voyager. But there's a ceiling, and that ceiling is enforced not by engineering limitations, but by something much more fundamental: energy. The energy required to accelerate a spacecraft to a meaningful fraction of the speed of light is absolutely extraordinary. Let me give you a sense of the numbers. Imagine you want to send a spacecraft massing about 100 metric tons, which is roughly the mass of a small space station, to a nearby star at 10% the speed of light. That's not even close to fast enough to make interstellar travel practical. But let's see what that costs. The kinetic energy involved is roughly equivalent to the total energy output of every nuclear weapon ever built on Earth, all of them, combined, and then multiplied several more times over. And that's just to get to 10% of light speed. To get to half the speed of light, the energy requirements scale up ferociously. This is not a technical problem that better batteries will solve. The numbers are written into the laws of physics. And then there's something even more mischievous hiding in those laws: Einstein's special relativity. Now I want to be careful here because people misunderstand relativity in a very particular way. They think it's complicated. It isn't complicated, it's just deeply surprising. Here's the thing: mass is not a fixed property of an object. As you push something faster, its resistance to further acceleration increases. We say its relativistic mass increases. As you approach the speed of light, this resistance grows without bound, infinitely. What that means in practical terms is that you cannot reach the speed of light. Not won't, not better technology needed. Cannot. It would require infinite energy. The universe is not hiding the speed limit from us. It's showing it to us very clearly. But let's suppose a civilization has figured out some incredibly efficient propulsion. Let's say they can convert matter directly into energy with perfect efficiency. That's the best case scenario allowed by physics, the theoretical upper limit. If you took the entire mass of the spacecraft and converted it completely to thrust, you could get to a decent fraction of light speed. But here's the catch: you need reaction mass. You need something to push against. And if you're burning your own spacecraft to move it, there's a point where you've burned more spacecraft than you have left, and you're not going anywhere useful. The Tsiolkovsky rocket equation, which governs all of this, is merciless. The mass ratio required for high fractions of light speed is absurd. We're talking about needing a spacecraft that is almost entirely fuel, hundreds or thousands of times more fuel by mass than the payload you actually want to deliver. Some people bring up the idea of a Bussard ramjet, a spacecraft that scoops up hydrogen from the interstellar medium as it goes. That's elegant in concept. The universe does contain hydrogen floating around between the stars, but when you work out the details, the density of that interstellar hydrogen is extremely low. You'd need a magnetic scoop the size of a continent to gather enough fuel, and the drag from that scoop likely cancels out most of the thrust you'd generate. It's a beautiful idea that doesn't survive contact with actual numbers. Now, I've been talking about classical physics limitations, but quantum mechanics adds another layer of nasty surprises for any high speed interstellar traveler. At significant fractions of light speed, even individual atoms floating in interstellar space become dangerous radiation. The interstellar medium is not empty. It has hydrogen atoms, dust particles, occasional molecules drifting around. At low speeds, these are harmless. At half the speed of light, those same hydrogen atoms hit your spacecraft with the energy of cosmic rays. A long journey through interstellar space at those speeds, without extraordinary shielding, would deliver lethal radiation doses to any biological passengers. The shielding required adds mass, and more mass means more energy required, and more energy required means the whole problem gets harder again. And here's what gets really interesting to me, the philosophical physicist in this. Even if you could solve all of these problems, even if you somehow cheated all the engineering away, the timescales involved change the nature of the enterprise entirely. At any speed a physical object can realistically travel, the journey from one star to another takes centuries or millennia. We're not talking about airline schedules. We're talking about a civilization deciding to send something, and that thing arriving long after the civilization that sent it has fundamentally changed, or perhaps ceased to exist. This is why I find the popular notion of alien visitors quietly funny, because it imagines that some civilization, perhaps millions of years more advanced than us, has solved all these problems and is casually zipping around the galaxy paying social calls. But the physics doesn't become negotiable just because you're old and smart. The laws of thermodynamics don't soften with technological progress. The speed of light doesn't budge. What you get with more advanced technology is better efficiency within the laws, not escape from the laws. Now, let me tell you what the speed of light barrier really means at a deeper level, because I think people misunderstand what relativity is actually saying. It's not saying that light is special because it's fast. It's saying something much stranger. It's saying that space and time are not what we intuitively think they are. They are connected. They are aspects of a single four-dimensional structure called spacetime, and the speed of light is not actually a speed in the conventional sense. It is the conversion factor between the space dimension and the time dimension. It's like asking what the conversion factor is between meters and seconds. It's a structural property of the universe, not a speed limit sign you could theoretically bypass. When you try to travel faster than light, you're not just running into a wall of engineering difficulty. You're asking for something that is geometrically inconsistent. It would require information and causality to break down. It would allow you to send signals backward in time, which creates contradictions so profound they would unravel the logical fabric of cause and effect. The universe, as far as we can tell, really does prohibit this at a fundamental structural level. There are speculative ideas floating around in theoretical physics, things like warp drives and wormholes. I want to address those honestly because I think it's important to be straight about what these are. A warp drive, in the theoretical sense described by physicist Miguel Alcubierre, works on paper by contracting space in front of a ship and expanding it behind. The ship sits in a bubble and technically doesn't move through space, so it doesn't violate the local speed of light. But the energy requirements to create such a bubble, as currently understood, involve quantities of exotic matter with negative energy density that are almost certainly larger than the mass energy of an entire planet, possibly a star. An exotic matter with negative energy density may not even exist in stable, usable quantities. We have seen hints of negative energy effects at quantum scales, the Casimir effect being the most cited example. But scaling that up to macroscopic warp bubbles is not just an engineering challenge. It's a physics question that currently has no affirmative answer. Wormholes, which are theoretical tunnels through space-time connecting distant regions, have an even more challenging problem. To keep a wormhole open and traversable, you need exotic matter to prevent it from collapsing. And even setting aside whether such matter exists in usable form, any attempt by matter or information to pass through a wormhole appears to generate instabilities that cause the wormhole to collapse before anything gets through. This isn't a solved problem. The equations that suggest wormholes could exist also tend to suggest they'd be extraordinarily unstable. I want to be careful here not to say these things are provably impossible. Physics has surprised us before, dramatically, but there's a difference between something being surprising and something being magically convenient. The history of physics is not a history of the universe making things easy for us. It's a history of us discovering that nature has its own structure, and that structure doesn't particularly care about our travel plans. There's one more thing I want to mention, which is the energy cost from a civilization perspective. If an advanced civilization is spending the energy equivalent of their entire planet's output just to send a probe to a neighboring star, that's a commitment of resources that strains credulity as a routine activity. Even a civilization millions of years old is still subject to the laws of thermodynamics. Stars have finite lifetimes. Galaxies have finite resources. The idea of casual interstellar tourism, of beings just hopping from star to star on a whim, assumes resources and energy availability that the physics of stars and stellar evolution simply does not provide. What the physics actually suggests to me, when I think about it honestly, is that interstellar travel is not impossible in principle, but it's so costly in time, energy, and resources that it would be among the rarest and most extraordinary undertakings any civilization could attempt. Not a routine activity, not something you do to satisfy curiosity about a small rocky planet. Something you might do once, with enormous commitment, over centuries, and perhaps only once in the lifetime of your entire civilization. So when people ask me, where are the aliens? Why haven't they visited? I don't think the answer has anything to do with whether they exist. I think the universe is almost certainly teeming with chemistry and biology, and perhaps with minds. But visiting, in the physical sense we imagine it, requires violating or circumventing laws that show no signs of being violable. The cosmos isn't hiding anything from us. It's just built the way it's built. And the way it's built makes the galaxy an enormous, quiet, physically separated place where the fundamental currency of travel is time and energy, and both are always in limited supply. That, to me, is not a depressing conclusion. It's a beautiful one. It tells us something profound about the structure of reality. The universe gave us the means to think and to understand and to ask these questions. It just didn't hand us a free pass on the math.